Welcome back. We are now on to developing methods for hyperbolic PDEs in 3 dimensions in vector unknowns. And specifically, the example problem we're working with, the canonical problem we're working with, is that of linear elastodynamics in 3D. What we've accomplished for this problem is a statement of the strong form and of the weak form. We'll pick up from there and write out the finite dimensional weak form and plunge directly into the matrix vector equations now. So we are doing, like I said, the problem of hyperbolic PDEs in vector unknowns. And in 3 dimensions. Okay, of course, these are all linear, right? So we're doing linear hyperbolic PDEs and so on. Okay, and also the canonical problem we're talking of here is linear elastodynamics in 3D. Okay, I'll directly write out the weak form, but the finite dimensional weak form, which you know really requires very little extra specification over the infinite dimensional weak form. Also, I will spare us the detailed writing out of the data here, right? We're very familiar with all of that now. All right. So the task we have here is to find UI sup H, and remember the H now indicates that we're talking of a finite dimensional problem. Find UI sup H belongs to the space SH, which is a subset of the larger space S. And particularly, we are thinking of SH as consisting of all functions UI sup H, and we expect these to belong to H1 over the domain, such that UI H equals UI given on the corresponding Dirichlet boundary, right? The part of the Dirichlet boundary that corresponds to that particular spatial dimension denoted by I. All right, we have this such that for all WHI belonging to VH, which is a subset of V, where VH consists of weighting functions WI sup H, also H1, such that WI sup H vanishes on that corresponding Dirichlet boundary. Okay, so find UI sup H such that for all WI sup H belonging to VH, the following condition holds, right? The usual integral equation, except now that we have the one extra term, right? The term that's second order in time. Okay, so we have integral over omega WI sup H rho, second time derivative of U with integrated over the volume, plus integral over omega WH I comma j sigma h ij dv equals integral over omega WH sub I Fi dV plus sum over the spatial dimensions 1 to 3 in this case, or NSD in general. Integral over the corresponding Neumann boundary WHI T bar I ds. Okay, that is our finite dimensional weak form, right? And I didn't state that anywhere, so let me just do this, right? So this is our finite dimensional weak form. Okay? All right. Now we know how things play out from here. Everything works out just as before, right? We're going to use the same basis functions. We're doing 3D, so you can think of trilinear hexahedra as being the simplest of those elements into which we decompose the domain. Everything works out just the same. Okay? Also note that each of these terms is going to give us our standard sort of contribution that we know so well, right? When we account for the fact that sigma h satisfies the constitutive relation right, which makes it truly linearized elasticity, right? What we get from this term is a very standard one that we've worked with at least once in great detail, right? So you recall that this term gives rise to C transpose KD, right? And these two terms here give us C transpose F. Okay. Also, now, when you recognize that the second time derivative, and it's a second time derivative, so I need a dt squared there. Right. When you recognize that this term on the left-hand side essentially involves the weighting function w multiplying the second time derivative of the trial solution, right? And you work through things just as we worked things out in the case of the parabolic problem in 3D. What you will see is that this gives rise to what sort of matrix? We have C transpose coming from W, and we're going to have a D coming from the U, right? In particular, we get a D double dot because we have two time derivatives on U. What is the matrix that goes between them? It's one we've encountered. It's the mass matrix. Okay? So essentially, this is the form that the matrix vector equations take in the case of linear elastodynamics. There's just one detail I want to point out here, which is something to do with the construction of M, because of the fact that our vector D has at each node 3 scalar degrees of freedom. There is one little detail about the construction of M which I'm going to show you right now. Okay? So let me just say here that we're going to look at one little thing to do with the form of M for this problem. Okay? And in order to understand that, what we need to do is consider the element integral corresponding to that term. Okay, so we consider integral over omega WHI rho second time derivative of UIH, sorry, there should be an H there and an H here also, dV, okay. We recall that, of course, this is simply a sum over the elements integral over omega e WHI rho second time derivative of right? Remember this, okay? So okay, we're going to work with just that element integral to clarify things.